Good evening, everybody. Welcome to BrisScience for May 2023, brought to you by the University of Queensland. We are so excited to be back. If this is your first time here, thank you so much for coming. BrisScience is a series of free public lectures on science where we aim to bring not just the best scientists, but also fantastic communicators to share their current science and the cutting edge of research with Brisbane and the world. I'm your MC for this evening, Joel Gilmore. And before we get started, I would like to acknowledge the traditional owners of the land on which we're meeting tonight and everybody watching on YouTube, and to pay my respect to elders past, present and emerging. It's a great opportunity to reflect on the efforts for those to protect and to promote Indigenous culture in Australia, and also the understanding of how to care for this fantastic land that we live on, which is so important to all of our scientific endeavours. So, couple of bits of housekeeping first. If you've got a phone, now is a great time to flick it to silent. But also, you can scan the QR code, which will pop up on your screen very shortly. It's on rotation. Because at the end of our talk this evening, we'll be taking questions over the question app. So you just type in your question there. You can do that as you go, or you can do it at the end. And we will then get through as many of those questions as we can afterwards. But we also have fantastic food and drink that UQ is putting on for us this evening. So we would really encourage you to hang around, to chat to our speaker and chat amongst yourselves as well, and make this a real cultural and scientific evening for us all. Okay, so tonight's topic. Well, if you think about the big things that we've been talking about over the last couple of years, I would say that viruses and AI are way up on that list, for better or worse, not in that order. And so tonight we are going to try and tackle both of those topics and also build on a little bit of a theme we've had running on BrisScience this year, which is mosquitoes. And we're going to be talking particularly about the diseases that mosquitoes carry, which are some of the deadliest in the world. And so to that end, it's my very great pleasure to be welcoming Dr Maggy Lord tonight. Maggy has a PhD in medical entomology, which was actually from Griffith University, but we don't need to dwell on that. And she now leads an international team that is studying detecting pathogens using light and artificial intelligence for quick and painless detection. So tonight, for some light entertainment that won't leave you in the dark, please put your hands together for Dr Maggy Lord.
People. I'm so excited to be here tonight to share our research findings with you all. My name is Maggy Lord, and I lead the infrared spectroscopy team at the University of Queensland. And today, I'll be telling you about our research findings, but before I do that, I want to tell you a little bit about myself and where I come from. I was born in Kenya, so I grew up in a malaria hotspot. And that means I had malaria a few times. And at the time I was growing up, the drug for treating malaria was chloroquine. Boy, oh boy, chloroquine is the most disgusting drug that has ever been developed. Until now, I actually don't understand why it was approved for use in children. It is so bitter. And I thought it was a punishment for us taking that drug. So I did question my parents, why do we have to take this drug? And Mom in response said, hey, look, if when you grow up, you can develop a cure for malaria, then we probably don't have to take this drug. I took that to heart, and ladies and gentlemen, here I am. Even though I'm not developing a cure for malaria, I hope that my research can help in one way or another to eliminate this disease. For the records, chloroquine was banned, not because I hated it, but because the parasites developed resistance. But I did celebrate when it was banned. Anyway, let's talk about what I do at UQ. So at UQ, I develop tools, so we actually develop tools that characterize mosquitoes, tools that can rapidly detect pathogens in mosquitoes, and tools that can detect pathogens in human samples, hoping that we can quickly identify when an outbreak is going to happen and stop it. So I'll start my talk by just showing you this slide. Mosquitoes are actually the deadliest animal on the planet. I don't know if you knew that. They kill twice as many people as humans do. Snakes come in third. That's true. They kill over 1 million people every year. And that is one other reason I'm passionate about working with mosquitoes and mosquito-borne diseases. So let's see some of the mosquito-borne diseases. They are out there. Of course, on top of the list is malaria. Malaria was eradicated in Australia about 40 years ago, but we do have mosquitoes that transmit malaria up in Cairns. So if something happened and people came into Australia with malaria, they got bitten by mosquitoes, there's a chance that malaria will be reintroduced in Australia. So we still keep an eye on that. Other diseases are dengue, chikungunya, yellow fever, Rift Valley fever, Zika virus. I'm sure you heard about Zika around about 2018. West Nile virus. These 5 actually are reported in Australia. Rose River virus is present in Brisbane, Bahama forest virus, Murray Valley, and we all heard about Japanese encephalitis, which was reintroduced in Australia early last year. And this just tells us that if conditions are favorable, these diseases might come back to Australia or might be introduced into Australia. So let's look at distribution of mosquito-borne diseases. Up there is malaria. Half of the world population is at risk of contracting malaria. That's 3.2 billion people. Dengue is also up there. 390 million dengue cases are reported every year. And we've got West Nile virus, which is reported in Australia, as well as Sub-Saharan Africa, and North Europe, as well as North America. We also have yellow fever, which is reported in Sub-Saharan Africa, as well as Southeast Asia. I'm just going to quickly go through some of the mosquito-borne disease facts. First facts. Like I said, over 1 million people die from mosquito-borne diseases. And over half of the world's population is at risk of contracting dengue, and that is 3.9 billion people living in 129 countries, and 390 million infections are reported every year. Zika is reported in 84 countries. That's 1 in 3 countries around the world. I think most of us heard about Zika when there was an outbreak in Brazil, but it is actually reported in 84 countries. And a case of chikungunya, it's a very hard one to pronounce, is reported every 4 minutes. Each year, malaria infects over 240 million people, and it kills over 600,000 people. 80% of those are children under the age of 5. And the worst of all, ladies and gentlemen, every minute a child is dying from malaria. Putting it in perspective, at the end of my talk, 60 children will have died from malaria. Okay, let's talk about science now. How are these mosquito-borne diseases transmitted to us? We will start from here. This mosquito here does not have blood. It just emerged from a breeding site, and it's flying around looking for a blood meal. It really just wants something for the eggs. It's very innocent. It finds this guy here. I'm just gonna go back. It finds this guy here. Oh, okay. This guy here is infected with some pathogen, let's say dengue. The mosquito bites that person, and then it gets infected here. So it's got blood meal in there. And then it incubates the pathogen for about, let's say, 12 days. And then when it finds someone else who is not infected, it bites that person gets infected. So that's how it works. But what we're interested in is finding these guys here so that we can break the transmission cycle at this point and finding these guys here so we can break that transmission cycle up there. And I'm just going to talk about mosquitoes a little bit because I love mosquitoes. I love age of mosquitoes. That's what I did for my PhD. So this is the life table of mosquitoes. What we are seeing here is 0 to 28 days just means the age of mosquitoes. When a mosquito emerges from a breeding site, it takes about 2 days to find a blood meal. No, fast. Actually, it emerges from the breeding site, it finds a partner. Once it finds a partner, it mates, and then it looks for blood. Once it's found blood meal, and that blood is infected, the pathogen will take about 12 days to develop inside the mosquito, which means mosquitoes are actually only infectious when they're about 12 days old. The rest of them are just harmless mosquitoes, which is why the age of mosquitoes is very important for us. That's what I did for my PhD. So what we do now is we try to shift the age structure of mosquitoes from the infectious ones, which are not many, as you can see, there's very few of them, to the harmless mosquitoes there. So all the interventions we see, the bed nets, the repellents, are trying to shift the age structure to the younger, non-infectious stages. And how do we do it? Like I said, age is very important. So we try and determine the age of mosquitoes. It's very hard. We do that by dissecting the ovaries of mosquitoes. We pull out tiny little ovaries and dissect them to see if a mosquito has laid eggs. If a mosquito has laid eggs, then it's probably infectious because it's probably picked up a pathogen somewhere. If it hasn't laid eggs, then it's a harmless mosquito because it did not feed on anyone. But that is very hard. I actually don't know how to do that. There's only one person who can do it. This guy here. Derek Charlwood. I had a chance to meet Derek Charlwood during my recent overseas trip. Derek is the only person who can dissect mosquito ovaries and tell how many times that mosquito has fed on people and laid eggs. It's so difficult that none of us want to learn. Actually, everyone sitting on that table is an entomologist. We had a chance to hang out with Derek for a week. Nobody asked Derek, oh, show me how to dissect mosquitoes. No, it's too difficult. So that's why we have to come up with alternatives. We can extract cuticular hydrocarbons from the legs of mosquitoes and potentially tell the age, but that's expensive. And given we are scanning lots of mosquitoes, it becomes very costly and time-consuming. We can also tell if a mosquito is potentially carrying an infection by using molecular techniques like PCR. So we extract stuff from the heads and thoraces to check whether the protein from the parasite is present. But that also requires costly consumables, and we cannot analyze 1,000 mosquitoes using that, especially when there is an outbreak and we quickly want to find that one mosquito. So that brings us to what we do at EQ. Our solution is infrared light. This is the work that I started working on when I was doing my PhD back in 2009. And we just wanted to see if we can predict the age of mosquitoes. Like I said, it's very important. So it was very attractive because this technique was already being used to predict the age of houseflies and other stuff with scientists from CDC and USDA in America. So we approached them and said, hey, look, if you can use it for houseflies, can we use it for mosquitoes as well? They said, sure, let's give it a go. And yeah, we started using it for mosquitoes. So how does it work? We actually just shine a beam of light on a mosquito, and we collect the spectral signature, and then we use AI to tell what's in that signature. So that signature carries a lot of information. So the science behind this is that, let's assume we have a mosquito carrying malaria and another mosquito that is not carrying malaria. The mosquito that carries malaria, the chemical structure of that mosquito is different from mosquito that is not carrying malaria because of the presence of the pathogen inside that mosquito. So when we shine a light, the reflected light is actually characteristic of the chemical composition of that sample, which is why the reflected spectral signature can vary between samples that, are carrying infection or not. So we use that hypothesis to see, firstly, can we predict the age of mosquitoes, and stretched the technique a little bit, can we detect infections in mosquitoes? And well, later on, I'll tell you how we're using it for detecting pathogens in humans. So for mosquitoes, like I said, we collect the spectral signature. We hypothesize that the signature is different for infected and non-infected samples. We then put the signatures into the computer and use AI. Obviously, we have to train the AI, tell them, hey, these mosquitoes here are infected, these ones are not infected. Can you develop a model to differentiate that? And once we have a working algorithm, then we use that algorithm to predict mosquitoes that we did not know. And it works pretty cool. So I'll show you some of the results that we have. Obviously, we started using it for age, and we showed that we could differentiate mosquitoes into different age groups. Obviously, we are interested in these guys here, the 19 days old mosquitoes, because they're the ones that are potentially infected. So if we can quickly detect those ones. By the way, it takes 5 seconds. I forgot to tell you. It takes 5 seconds to shine a light, collect that spectrum. And once you have the algorithm working, it takes, let's say you have 1,000 mosquitoes, it takes 10 seconds to analyze those mosquitoes. So it's pretty cool. And then we did mosquito species, and why is mosquito species important again? I'm going to tell you a story why. So we need to know the species that we're working with. So in Tanzania, for example, there's two species that look the same. We call them cryptic species. When you catch them, they actually look the same morphologically, but they behave very differently. One of them bites inside, and one of them waits for you while you're outside. I have no idea how they decide to do that. But obviously the one biting inside will be killed by mosquito nets. When it lands on a mosquito, when it's trying to find you when you're sleeping, it will be killed by bed nets. And the one feeding outside, because it's smarter, it would not be killed by the insecticides. So what we did is we just assumed, hey, we have bed nets and we have two species and the bed nets are killing both species. No. What happened was the mosquito that was feeding inside was actually eradicated. And because we were not doing any species composition checking, we later realized that, hey, bed nets is actually not working because there's only one species left and it's biting people outdoors. So it's very important for us to know the species that we're working with for that reason. So we can differentiate the species. We've worked with the most dangerous mosquitoes in Africa to see if we can differentiate, and we could differentiate those ones. Wolbachia infected mosquitoes. Wolbachia was actually a technique that was developed in Australia at the University of Queensland. What scientists did was they introduced the bacteria into the mosquitoes, and this bacteria blocks transmission of dengue. So they artificially introduced it and released the mosquitoes up in cans. And these mosquitoes are meant to mate with the wild population and transfer the bacteria to the wild population. But for us to know whether they have actually transferred the bacteria to the wild population, we have to catch the mosquitoes, analyze them. We can use PCR, but we won't analyze a lot of mosquitoes. So we trialed it on Wolbachia-infected mosquitoes, and we could differentiate Wolbachia-infected mosquitoes as well. And trips, that word is so long, so I'm just gonna call it trips, trypanosoma. It's a parasite that is found in South America, transmitted by kissing bugs. And people get infected when the kissing bugs, the fecal matter from kissing bugs, when people accidentally rub them in their eyes. So we wanted to know if we can use our technology to firstly detect the kissing bugs that have the infection, and also see if we can detect the infection in the fecal matter from the kissing bugs, and we were able to do that. And Zika, this was very big news for us. The work was funded by USAID at the time when Zika was a big thing in Brazil, and they just really wanted to see if infrared and AI can quickly detect Zika in mosquitoes so that we can they can know where these mosquitoes are to stop, transmission from mosquitoes to people. And just as an add-on, we can tell mosquitoes that are infected with dengue from those that are infected with Zika, or we can actually infect one mosquito with both dengue and Zika, and we can differentiate which one is infected with both, or which one is infected with just Zika, or which one is infected with just dengue. So that was cool for us. So we might be wondering why all this? How can we use it? So I'll just summarize why this is very important for mosquito control. This innovation is very important because by knowing the age of mosquitoes we collect, we can tell if the interventions are targeting harmless mosquitoes or potentially infectious mosquitoes. And by knowing the species of mosquitoes, we can tell if interventions are effective against one species and not the other, or if it's killing both species. And obviously, if we catch infected mosquitoes, it's a bad sign. It could mean that there will be an outbreak in this place, so please pull out all your interventions so that people are protected. We can also monitor insecticide resistance, and also, obviously, novel interventions like Wolbachia to see whether they are working. Now, let's move on to the work that I've done with human samples, and I'm gonna focus my talk tonight on malaria. We have worked with other pathogens like dengue, but I thought that the malaria work, the findings that we have, will be more interesting to share with you tonight. So the malaria work obviously came from, from our mosquito work. We thought, well, if it works for mosquitoes, then we should probably trial it on malaria. And at the time, we thought about using it for malaria was when WHO came up with a strategy to eliminate malaria in 2015, and they actually wanted to eliminate malaria by 2030, which was very ambitious. And to do that, they want to test everybody with suspected malaria and pretty much scan everyone in a village. Like, they don't know who is infected, so we just need to know who is actually carrying the parasite. The issue we have with malaria is asymptomatic patients. These people do not have symptoms. They walk around very healthy, but mosquitoes love them so much. So mosquitoes will go bite them, pick up the infection, and the kids are the ones that die from the disease. So if we can find these people, we probably will reduce malaria transmission by 90%. Or 75%, because they are actually responsible for up to 75% of malaria transmission in some areas. Obviously, in 2022, because not many tools had been developed, WHO declared that this strategy has stalled, and we need more tools to help with the elimination of malaria. And so the new target is actually 2040. But to do this, effective malaria diagnostic and surveillance tools are required to facilitate universal testing. And like I mentioned, we need to find these people who are infected and get them treated. We quickly need to find where asymptomatic patients are. If I didn't have any symptoms and someone came to me and said, hey, look, I want to test you. Like, why are you testing me again? I'm feeling all right. So we need to come up with tools that are more friendly to asymptomatic patients, and this is why we decided we will trial this technique and see if it can have a use case for asymptomatic patients. So the reason why we have to develop new tools is because what we have is not sufficient. So far, malaria is detected, or the diagnosis of malaria is traditionally done by microscopy, which is you prick someone, put blood on a slide, look under a microscope to see if you can see malaria parasites. But only experts can do that, and they can count how many parasites there are accurately. Well, an estimated amount of parasites. So sometimes they miss out, especially in areas where there's low transmission. And we have rapid diagnostic tests as well. They're very easy to use, but because malaria comes in different forms, there's different parasite species, these rapid diagnostic tests sometimes cannot pick up this, and when the parasite load is low, they tend to miss out some of these people. And obviously we can use PCR, but it's costly. We cannot afford going out, collecting blood from the whole village and using PCR to detect malaria parasites in people. It's just not feasible. So from our mosquito studies, we determined we could detect pathogens without destroying the mosquitoes. So what did we learn from that? If we can do that with mosquitoes, can we do this with humans as well? I did share this idea with the big funding body, and they told me, it's not going to work, so don't bother doing it. So I said, okay, I understand, but I still want to try and see what I can achieve so that I don't say I didn't try. Malaria infects the red blood cells. So our hypothesis was, if malaria is in the red blood cells, it's changing the configuration of red blood cells. Then if we shine a light onto someone's finger and we can see that light popping through, it's pretty much like using a torch on your finger. You can see the light coming through, right? So this is exactly what happens with our technique. You shine the light, it picks up whatever is inside the red blood cells and then projects a spectral signature. So we thought, yes, we will try. Because of that reason, we're shining through red blood cells that are infected with malaria. And then obviously use artificial intelligence to differentiate those that are infected from those that are not infected. But to demonstrate this, we had to do a series of experiments. And I'm going to use terms here that I thought I should define beforehand before I dig deeper. So I'm going to talk about sensitivity in my next few slides. And whenever you hear that word, it simply means the number of people with a disease that are actually correctly identified as having the disease. And whenever I say specificity, it means the number of people without a disease that are correctly predicted as not having the disease. Obviously, a screening tool, if we're going to go out to screen a village, we want something that is highly sensitive, that we can at least get 95% of the people that are infected. Okay, so here is near infrared again. What we needed to do first, we were not just going to go out in the field and start scanning people. We needed to do a series of experiments. This work here was done in partnership with the Australian Defence Force, the Army Malaria Institute, and they've been very valuable in providing samples in most of the experiments. So our aim here was grow malaria parasites in the lab. Yes, we can grow malaria parasites in the lab, and then use infrared and AI to differentiate red blood cells from red blood cells infected with the parasites from those that are not infected with the parasites. And because malaria comes in different stages, stages that infect the liver, there's stages that infect the red blood cells, we also wanted to see if we can use infrared light and AI to differentiate those stages of malaria, which we grew in the lab as well. We also wanted to see if we can quantify these parasites, like how many parasites are actually in that drop of blood, because it's very important to know how sick someone is. So we needed to do that. So this first slide here is simply telling us that we had so many infected red blood cells, and we managed to differentiate them from very few uninfected red blood cells. And actually the technique was 99.9% sensitive. It was almost 100% specific at that point. So at that point, we're like, yes, cool, this thing works. Let's move on to the next one. Can we differentiate these different stages? So there's rings. Rings are the ones that are identified in red blood cells. If someone pricks you and they're like, okay, let's test you for malaria, they see rings in your red blood cells. So can we differentiate the rings from stages of the liver and stages just before the red blood cells? And as you can see, yes, we could differentiate them. And then we moved on. Can we then quantify these parasites? Yes, we could. I would just bring your attention to here. This is when the we have nothing in the parasites. They're not infected. And this is when the parasitemia is very low. This is when parasitemia is very high. So you can see we can clearly tell the difference between this high and this low parasites for the different stages. It's not very diagonal line, but that's as good as it can get, I promise. And so we still were not ready to go out and scan people. The next thing for us was to see if this technique actually works non-invasively. And the next step was to infect mice in the lab, still working with the Australian Defence Force, and wait for the parasites to rise within the mice and scan them periodically. The objective was, can we differentiate mice that are infected from those that are not infected, and can we differentiate mice that are infected with very, very high parasite load from those that are infected with very low parasite load. Just from the look of the spectral signature, you can see the blue one is all the mice that were not infected. So it clearly stays away from the ones that are infected. 72 hours post-infection means the parasitemia or the parasite load was really high. And 48 was middle, and 24 hours, it was still very low parasitemia. At this stage, we can't really tell. This is where we bring in AI. AI is smart at that point. So what we do is take the spectral signatures, put it into the computer, and tell the computer to tell us the difference between infected and uninfected, and differentiate those that have low parasitemia from those that have high parasitemia. I didn't want to give you too much details, but we also needed to show that by scanning the mouse and taking the blood sample from the mouse, we got the same result, because we were not going to convince someone that we're just scanning you and we get the same result as person that, gave out the blood sample. So we did both. We scanned the mouse and took blood out, and scanned the blood and compared the two. And what we're seeing here is sensitivity for when the blood was taken out of the mouse at really high parasitemia. It was 95%, which means out of 100 mice, 95% of them were correctly predicted. And when we scanned mice non-invasively in the ear, we got the same sensitivity. So we were like, yeah, this is cool stuff. Now there's no difference between scanning blood and scanning the mice non-invasively. So we were very excited at this point. And just the specificity was 84% when we took the blood out, and was 86% when we scanned the mice non-invasively. We obviously, like I said, we're looking for really high sensitivity, so this was good news for us. But still, the parasitemia was low. I haven't shown you results for when parasitemia was lower, but scanning mice when parasitemia was lower was better when we scanned them non-invasively than when we took the blood out. So that was pretty good. And at that stage, we were very confident. We are going out to the field to scan people now. So this work was in partnership with Oswaldo Cruz in Brazil, our long-term partners. So they went out to the Amazon and scanned people that had malaria. And we developed a model and used that model to predict the ones that were not put into the model. And we got sensitivity of 100% and specificity of 87%, which was really good. I'm getting close to finishing. But we needed to show that by scanning people, the biomarkers we are getting are actually related to the parasite. So what we did, we also scanned purified parasites to show that the biomarkers that we are seeing when scanning people, through the skin are the same. So like here, you can see this is purified parasites, and you can see a little peak there, and another one there, another one there. They're corresponding to the ones that we saw when we scanned people non-invasively. So that was a very good sign that what we're seeing when we scan people, we scan people's fingers or ears or arm was what was expected to be seen. And ladies and gentlemen, that's where we are right now. Our future work is to validate this work in multiple field settings. So I'm just setting up this in different countries now. We want to determine the effect of mixed infections, skin color, age, gender, parasitemia. Do they have an effect? Because it's just a lot of variance that we have to consider when developing predictive algorithms. We also want to integrate this into a disease advisor platform, which tells people in real time when they're at risk of contracting an infection. You can have a look at the platform if you just search disease advisor. And also we want to assess the capacity to detect other diseases like dengue. We have done pilot studies. My PhD student just showed that we can use a technique to detect dengue in blood as well. And we're working with our partners in Brazil to scan people non-invasively to see if this technique can be used for that purposes as well for dengue. And can we use wearables for this? I am gonna try, and see if it works. So hopefully we can, integrate this into, web platform and use wearables like smartwatches to, continuously scan. And when there's a signal for an infection, then the user will be alerted, hey, go see your doctor. You might have something in your red blood cells. And just want to quickly acknowledge that this work would not have been, successful without the funding from NHMRC funded our human experiments, and Advanced Queensland gave me a fellowship to do the work with humans as well. USAID, Bill and Melinda Gates, Government of Canada funded the mosquito work, and we are working with Oswaldo Cruz in Brazil, CDC in the US, USDA in the US, Ifakara Health Institute in Tanzania, QUT, and the Australian Malaria Institute. And I just want to quickly say thank you to the organizers for giving me this opportunity to share with Joel and Dominic. Thank you so much for making this happen. I also just want to say thank you to my family. They've been very patient with me, very understanding. Sometimes I've been away for over 2 weeks trying to set up these experiments overseas, but they have been very good. My partner, Anton, here, thank you so much. And there's someone here who is very interested in helping out. She said she wants to be a mosquito doctor. That's my daughter, Lulu. This photo was taken when she was 5, at kindy. And when they asked her, what do you want to do? And she said she wants to be a mosquito doctor like mommy. She still wants to be a mosquito doctor, she said.
Amazing. Thank you, Maggie. We'll give you a moment to catch your breath. We'll pop up that QR code onto the screen. Maybe. So normally there's a dramatic moment where the QR code pops up, All right, alternatively, you pull out your phones and go to, what is it, bit.ly/BrisScience, capital B, capital S. Hey! BrisSci QA, I was so close. Oh, that's like good things, all things in life, easy come, easy go. Don't forget, you can watch all of these BrisScience talks on YouTube, so you can catch up on this talk and many others. And we will, of course, be back next month. So make sure you sign up to our mailing list. Head to Facebook or the UQ BrisScience website, or I think we're still on Twitter. I don't know who's on Twitter anymore. It's hard to keep track with Elon changing every day. All right. No, we're not quite there. Well, there's a few questions here, so I'm going to start on these questions. And there it is. Grab it while you can. Oh, there you go. Too slow. Okay, here we go. Are you up for some questions?
Yes,
amazing.
I am.
All right, so the first question is from George, which is, what is the cost of carrying out the spectroscopic investigation? And maybe I'll broaden that to you, maybe what's the cost today, but also what's your long-term thinking?
Long-term thinking. So the cost right now, obviously, we need an outlay for a spectrometer. With the mosquito work, we started with a benchtop spectrometer, which was expensive, like $60,000 US. But in the long term, it's actually more cost-effective, because once you've scanned, say, 30,000 mosquitoes, then it becomes cost neutral, or you don't need any consumables, so you don't have to spend anything after you've analyzed 30,000 mosquitoes. However, we are trialing the use of small spectrometers, which are $2,000, and obviously if we're going to scan a whole village in one day, that's going to be nothing compared to PCR, which costs $15 per person.
Amazing. Okay, we've got a question from Bobby here who asks, can this approach work for other diseases?
Yes, I think so. So we were not the first one to do this work. We actually just followed footsteps of other people. Like I mentioned, they were using it on house flies before, but infrared is actually used for diagnosis of cancer as well. Yes, it can be used for other diseases. We are using it for a range of diseases at UQ. We are scanning, soil transmitted helminths and other mosquito-borne diseases as well.
Great. We've got a couple of questions about the mosquitoes themselves. So Gemma asks, first of all, amazing technology, but then says, just curious if the eggs laid by infectious mosquitoes are infectious.
We are yet to prove that, but I would say no. It does not transfer the infection to the mosquitoes, to the eggs, otherwise we'll be in trouble. Like every single mosquito that emerges will be infected and there will be infections everywhere, so no.
Okay. Emerald asks, why are mosquitoes able to carry these diseases without being affected?
They are affected, actually. Once they have the infection, that infection makes the mosquito want to bite someone. So it's like probing the mosquito, go find this next person and transfer me to the next person. So it does affect the behavior of a mosquito in one way or another.
Great. Alban and Luke asked questions around what type of AI did you use and who did the training?
So we've used a whole bunch of them. We've used PLS. We're using artificial neural networks at this stage because they seem to be better for our spectral data. My partner there is an AI expert, so I've asked him to run some of this stuff. He can answer that question. But anyway, sorry, I'm putting you on the spot. Yeah, so we're using artificial neural networks for spectral data because it works well, and we do it ourselves. Taranga there is my research assistant. She's very good at running artificial neural networks for this kind of work.
Amazing. And Sitha Choke also asked that question, so apologies for not mentioning you before. Okay, we've just had a whole mass of more questions come in. Let's see. This is the most stressful part of my day. Kathy asks, you mentioned that skin colour will be investigated in future studies. For your current data, do you scan people within a certain Fitzpatrick scale? And then what studies do you think what challenges might you think you encounter in the future?
Look, we think that skin color is going to be one of the issues that we need to deal with. But I am confident that with AI is pretty smart. We can regress out skin color, but we need the data to do that. In Brazil, they scanned indigenous Brazilians, which seem to have the same skin color. So we didn't have a great deal of data to work with. But yeah, we hope that even if it's an issue, we can use AI to solve that problem.
Right. All right. Well, we might just ask a couple more questions because I know that food is outside calling to us all. But Izzy asks an interesting one. Couldn't we just wipe mosquitoes off the face of the earth? Or would wiping them out cause some problems? And I know there's been some serious discussion about this, but I'd be keen to hear your thoughts.
Look, I wish we could. These mosquitoes are very smart. Do you know where let's just talk about the infected ones. It's very hard to catch the infected ones. Why? Because we don't know where they hide. They are very smart. I'll give you an example. In Africa, we come up with new interventions all the time. Why? Because mosquitoes are pretty smart. They just evolve resistance and then just run away from the interventions. So no, I don't think we can't get rid of mosquitoes because they know how to hide. They will run away from us.
And can I suggest that nobody mess with Izzy when you're going out to the foods? And maybe a related question, Kerry asked, will diseases like malaria always evolve to beat our drugs and defences? And I guess you've sort of had a bit more hopeful view, but I'll...
Well, yeah, it has, like I said, chloroquine was working so well, and the parasites develop resistance. So parasites are looking for ways of, running away from all these drug interventions. The reason why we actually don't have a malaria vaccine that is, effective, because the parasites themselves are very smart, and they come in different stages. So if you target one stage, there is another stage that you need to deal with. So yeah, that's a big problem we have. And once you have a drug, then there is resistance developing with that drug. So we have to keep innovating.
All right, so almost last question. Let's say the federal budget, they decide that actually, we don't need another submarine. We'd actually like to invest in, science. And they gave you a blank check.
Oh.
What would you do? What would be your next steps?
I would love to progress the work that I've started, because I feel like it has potential not just for malaria but for other diseases. I'd love to see that people that require this technology have access to it, and they actually can get it without having to pay a lot of money. So I will invest in developing wearables for detecting infectious people.
Very exciting. And then my last question, which actually...
This is the last one, right?
This is the last one.
Okay.
Because I asked the speaker last month this as well, is do you use your grad students to feed the mosquitoes?
No. Can you confirm? No.
That's right.
I
The answer's
actually
no.
used to. No, I used to feed mosquitoes by I have a photo somewhere, put my arm in a cage full of mosquitoes, and 1,000 of them will land on my arm. And I have to stay there still, like I can't move my arm because I'm gonna interrupt their feeding. So stay there still for 15 minutes for them to feed on me. And then, then they will fly away happily. And then I have mosquitoes to work with and continue with my research.
The sacrifices you're making for your science. Thank you so much for that. Give a huge round of applause to amazing Dr. Maggy Lord.
Thank you. Oh, thank you so much.
Thank you so much for coming out tonight. We'd love for you to join us for some food and drink. We'll have the side doors open up there as well. Try not to crush yourselves on the way out, and we'll see you all next month. Thank you.